I welcome you to this lecture of electrohydrodynamic atomization, which is also commonly referred as electrospray. What we have here in this slide is there is a deformation of meniscus near a charged plate. What we mean by this is if there is a liquid sitting there and if you bring a charged plate next to it, you see that the meniscus is deformed. By that what we mean is that you will see that the meniscus takes the shape like this. Okay. This deformation of meniscus near a charged plate, that happens because counter ions in double layer driven along the interface towards the meniscus tip. I mean one immediate event that happens because of this deformation of meniscus is that counter ions in double layer driven along the interface towards the meniscus tip. Okay, and what eventually this will lead to is a high charge density near this meniscus tip, a high charge density at this meniscus tip. When this charge repulsive force, when this is greater, when this charge in this repulsive force, if I look at the slide, when this charge repulsive force is greater than the local surface tension, then we generally see something called a Coulombic fission and draining of charge by extrusion of liquid jet. So, what eventually what this means is that you have a droplet, and that has because of the presence of this electric field, there is a high charge density at the meniscus tip, and then this meniscus tip, there would be this charge repulsive force within this tip. When it is higher than the local surface tension, this droplet cannot hold that portion. There would be a Coulombic fission, and the only way the charge can drain is if there is a liquid jet that extrudes from this tip. Okay, now this idea has been used in something called a cone jet mode electrospray. What is done in this cone jet mode electrospray is there is a metal capillary, this is the end of the cone, and then there is a grounded plate. Now, you have here this is the circuit that you have. So, what you see here is that the liquid jet emanates from this tip, and this liquid jet breaks down into small droplets. Okay. So, what you have here, so what we are trying to do here is, what we are saying here is, if so liquid is coming from this side, if liquid is in a metal capillary, then a conical, then a meniscus appears at the orifice, I mean to say this place, at the orifice when a voltage is applied. Voltage is applied across this point and this point. So, then automatically there would be a meniscus appearing. So, what we see here is that what we will see here at this point is that there will be a double layer forming here, and what is important at this point is something called a time scale. In this operation, there is it is important to look into the time scale. What I mean by this is that this double layer, it has certain time to form. There would be something called a charge relaxation time. I mean, you have to, when you apply the voltage, there would be the charge, they have to align themselves next to the wall. That requires certain amount of time, and that time is different. If you expect an electron to align, or if you expect an ion in an electrolyte to align, or if you expect a big polymer molecule to align, that time is different. So, it requires certain time, and at the same time you have something called an hydrodynamic time scale, where I mean the liquid is flowing. Okay, so how much time it takes for the liquid to flow through this capillary. So, if these time scales are not matched properly, then you cannot expect then equilibrium exist in that double layer, and it is important to have that equilibrium existing in the double layer. Now, if we try to look at the time, this relaxation time that I have been talking about, if I look into it further, what I see here is that this electric double layer, I think by now you all know that this electric double layer that has something called a d by length, that is given by lambda d is equal to square root of epsilon r t divided by 2 f square z prime square c infinity. And you know what are these terms, because these we have already discussed in connection with electroosmosis. F is here the Faraday constant, which is nothing but the product of Avogadro number and elementary charge of an electron. So, these two product of these two quantities, that is what is F, and this Z prime is the ion valency, that is how we look at it. And so, in this case we have a lambda d, which is called a d by length. Okay. Now, I expect the ion to travel over this lambda d. I mean, if this equilibration of double layer, if that has to happen, ion has to travel over this distance. So, what we see on the other hand is that a current can be written as sigma into E, which is nothing but this quantity, where sigma is given as sum of, for all components, lambda I C I. What is sigma here? Sigma is, let me point out, here we have to note two terms which are important. One is epsa, which is permittivity, that we have already studied in connection with electroosmosis. On the other hand, this sigma, this sigma is basically the conductivity. This sigma is conductivity of the electrolyte solution. So, this is permittivity and this sigma is the conductivity. So, conductivity is reciprocal of the resistance. So, you can see I is equal to sigma into E and E is del of phi. So, this we understand, and then sigma, I mean where the conductivity is coming from, if you look at it, then this sigma is basically the molar ion conductivity, that lambda I is equal to lambda I is molar ion conductivity as far as this ith ion is concerned, molar ion conductivity as far as this ith ion is concerned, and this Ci is ionic concentration of species, ionic concentration of species I. Okay. Now, if we are looking at a symmetric, if you are looking at a symmetric binary electrolyte with ion concentration of C, okay, so ion concentration of C, if you are looking at, then you write sigma as equal to lambda plus lambda minus into C. So, this is for symmetric binary electrolyte. With ion concentration C. Okay, now here we have another term, that is lambda I. So, we understand sigma, we understand Ci. Now, lambda I, or in other, here we are talking about lambda plus and lambda minus. This lambda I, again in turn one writes lambda I as lambda I said is molar ion conductivity, that is equal to lambda I is molar ion conductivity, that is equal to F square Z I prime square V I, okay, where this V I is in turn the related to the diffusivity of the ion. V I is equal to d I divided by R T. Okay, so, this molar ion conductivity, so that will have a Faraday's constant and the valency, that part is taken care of, and then a velocity which is arising from the diffusivity of that particular ion. Now, for a fully symmetric, for fully dissociated symmetric binary electrolyte, if I write or if I go to the next page, for a fully symmetric, for a fully dissociated symmetric binary electrolyte, d is equal to d plus is equal to d minus. We are talking about di. So, here since we have brought in this lambda, lambda plus and lambda minus for symmetric binary electrolyte. So, by the same token you will have d plus and d minus, and both would be equal to d for a fully dissociated symmetric binary electrolyte. So, we given this information, now if somebody tries to find out what is the time required, if somebody wants to find out what is the time required for an ion to diffuse through d by length. Okay. So, that can be given by, in that case, TD, let us say, that would be close to lambda d square divided by d I, lambda d square divided by d I, okay, because d I is the diffusivity of component of species I, of that ion I, diffusivity of that through that Debye layer, and lambda d is the length. I mean basically we are talking about a length scale and the velocity at which that will go through that length scale, and from that we are trying to find out what would be the time scale, what would be the order of time required for an ion to go through this distance. So that is basically lambda d square by d I, and if somebody works with this, I mean I have already we have talked about lambda d here. What is lambda d? Lambda d is square root of this quantity that we have already we have studied this earlier as well, and this part is the sigma. So if somebody works with this and this sigma in turn is related to the di. Okay. So if somebody works now with to find out what would be the lambda d square by di in this case, you will find that lambda d square means you had lambda d as square root of epsa RT by 2 f square z prime square c infinity. So lambda d square means the square root would be gone, and on the other hand if you look at what you have in sigma, you will find that sigma contains those other terms there as well. Sigma contains lambda, right? Sigma is a function of lambda, and then lambda, this is the molar ion conductivity, and that contains these f square z I prime square etc., and then you have di. So if somebody works through this, he will find out that all these terms will cancel out, this f square z prime, and here you have sigma plus lambda plus and lambda minus for definition of sigma. So you will find that this will cancel out, and you will have this TD left, you are left with TD is equal, this quantity is equal to epsa divided by sigma. That means this is the ratio of permittivity of the electrolyte solution divided by the conductivity of electrolyte solution. Now if somebody looks into what are the typical permittivity and typical conductivity of the materials that one works with, you will invariably find that this comes to about 10 to the power of minus 6 second. 10 to the power minus 6 second. I mean of course this is of the order, I mean 10 to the power minus 6 means it can be between 10 to the power minus 5 to 10 to the power minus 7. That means this is basically 10 microsecond to 0.1 microsecond. So this is the time required for equilibration of an ion if you through this Debye length. Okay. Now here you have another time scale. See what you are playing with. If you have to atomize this way, that means you are having a liquid flow, and at the same time you are developing some charges within these within this solution. So if you expect that these two expect that that this equilibration within the Debye length happens much faster than much before the liquid is flown out of it. So then in that case, this time scale has to be compared with what you call the viscous time scale. Viscous or the complete term would be viscous diffusion time scale, which typically referred as R square divided by mu by rho, where R is the capillary dimension. So this is typically a viscous diffusion time scale, or if somebody wants to work with a what you call a hydrodynamic time scale, one can write it this way as well, hydrodynamic time scale, which would be equal to L is the length divided by u, which is the velocity, which is something like R square L by Q. Q is the flow rate, R is the capillary dimension. So that is also possible, this hydrodynamic time scale. And what you have to ensure is that this viscous diffusion time scale has to be greater greater than this. That means this should be shorter, this Td, the time required for these for these ions to relax within this Debye length, that has to be shorter by at least couple of orders of magnitude, because then in that case the flow will happen and the equilibration will happen instantaneously. So you do not have any issue with okay, it has not been equilibrated, ions have not formed properly, but you are forcing the flow to go out. I mean it is not that way. So then you can use the full potential of this mechanism. So these time scales are extremely important. These time scales are extremely important. I mean if I try to articulate this further, if this time scale, if this Td is much less than this viscous diffusion, if this is much less, what you can conclude from here is that the double layer exists in equilibrium. Double layer exists in equilibrium. In other words, so what you conclude here is that sufficient I would say residence time to charge double layer when jet moves out of capillary. So this is ensured, these issues are addressed if you have this time scale, this is less than the viscous diffusion. Fortunately, this viscous diffusion typically people have for R is equal to say if we are looking at 0.1 millimeter, then these will come to this time scale, this viscous diffusion time scale typically will for common materials that will handle, these will come to about 10 to the power 4 microsecond. So we were looking at 10 to 0.1 or maybe 1 microsecond, 10 to the power minus 6 second for that time required for an ion to diffuse, whereas the viscous time scale is much higher. So when this is much higher, so that means the equilibration of double layer will happen. I mean, this time scale appears almost instantaneous compared to the flow of this liquid, the viscous, as far as the viscous effect is concerned, and this is extremely important. If these two time scales are not adjusted, then you cannot leverage this idea. So, as a matter of fact, I mean, since we are into this relaxation time scale, I mean, we need to understand this time scale, or rather we will address this time scale once again at a later time, because these we have so far assumed that this is a DC electric field. Okay, now if one has this AC, if there is a AC field, if there is another time scale involved, within that time scale the voltage changes, so then that time scale also will become important for these for this mechanism. So, this AC time scale, and AC time scale, what defines AC time scale is the frequency, how many hertz. So, what frequency you have, that becomes important. And then what we will try to do at that time is we are trying to find out what is the RC time scale. Basically, see the time required for diffuse through Debye lens. So, these double layer, that can be expressed as a circuit like a resistance and capacitance. For example, a resistance and capacitance, they are acting parallelly, because this electric double layer, that has its own resistance arising, since you have seen there is a sigma involved, and at the same time there would be some amount of capacitance as well. So, you bring in that resistance capacitance type model. I mean, instead of looking at the double layer, you simulate that with R and C and find out what is the time scale for that RC circuit, and that is referred as the RC time scale. So, this RC time scale will be compared. I mean, if you had an AC field operating, then that has its own time scale, and where that stands with reference to the time scale of these diffusion of these ions. So, that is another aspect, another issue that will come up. Okay. So, basically if we go back to, I mean, where we started on these formation of we are trying to find a mechanism by which the electrospray will happen, and we found that there is an issue of this time scale. I mean, that is appreciated. So, there could be, so if I look at the slide, there could be a DC electric field or an AC electric field, either way it is possible. For DC electric field, whatever we talked about is fine. For AC electric field, there is another time scale coming in because of the frequency. Now, what we must understand here is there exists something called a critical voltage. I mean, of course, we are in this DC regime. I mean, first we are talking about the DC field, not the AC field. We will look into some aspects of these later. What we have here is something called a critical voltage. The critical voltage is, if I try to derive it here, the critical voltage see this, the liquid, if we look at the liquid meniscus, that protrudes from the orifice, if you assume that this is basically of the shape of a spherical cap, if this is considered as spherical cap, then this is equal to, then this will be sigma by, so then the stress arising from surface tension, that is equal to sigma by r, where r is basically, you know, principal. I mean, you understand what this is. This is of the same order as radius of the capillary. We are doing just an order analysis here. I mean, at what we need 10 to the power 5 volt or 10 to the power 8 volt, that kind of analysis we are doing. It's not a rigorous analysis either. And so this is of the order of, if we try to look at the order, this would be about 10 to the power minus 3, 10 to the power minus 3 meter. That means we are talking about, say, 1 millimeter. And if somebody looks into the imposed Maxwell stress, then for applied voltage V and electrode separation D, Maxwell stress, imposed Maxwell stress would be EFSA into V square by 2D square. Okay. So, if the stress arising from surface tension is greater than the Maxwell stress, then that droplet will not come out. So, this Maxwell stress, these has to be greater than, this quantity has to be greater than this sigma by r, then only the drop. I mean, we are talking about the order, by order of magnitude, these has to be greater than this, then only you can expect the droplet to come out. So, if that is so, then you can come up with what would be the critical voltage. I mean, what is the minimum voltage that you should have. Okay. So, if you equate this two, and if you remove 2, I mean, if you try to find out the order, you can take sigma as 10 to the power minus 2 Newton per meter. D is the distance between the two, and distance between the two can be taken as, say, 1 centimeter. That means, what distance we are talking about? We are talking about distance between the two electrodes. We are talking about this distance. Okay. So, this distance is, let us say, 1 centimeter, and then EFSA is commonly taken as 10 to the power minus 10 Coulomb square by Joule meter. So, in that case, you will find this critical voltage. This critical voltage will come to the order of, this critical voltage will come to the order of kilovolt. Okay. Say it can this is of the order of kilovolt. Okay. Not simple volt or not megavolt, it will be of the order of kilovolt. So, that is something. So, there exists such a critical voltage. So, if somebody wants to know, okay, for conventional applications, for conventional, the materials that we have, if we want to create droplet by this mechanism, what kind of voltage we have to create between the electrodes, and this is something which we have. So, there exists a concept of critical voltage. Of course, this is just an order analysis. One important thing you must understand, I mean, if you do such, if you go by this kind of the route, what we are neglecting here is the space charges, because there would be, if the solution itself, if the solution that is flowing, so this part is, this is neglected. So, if the solution that is flowing is conducting, if the solution that is flowing is conducting, that means there would be cation accumulation at the meniscus tip. So there would be some difference, there would be some difference, there would be some change to this critical voltage. Okay, so for a conducting solution, there if the solution that is flowing is if it has its own space charge, so that has to be so that will affect this analysis. Now, once the jet comes out, once the liquid meniscus come out, here we have another issue here, subsequent breakup of jet, which is basically there are two ways this jet can break up. One is by Rayleigh capillary instability and the other is Coulombic instability. Let us try to understand. This is the cone, and this is from which the liquid is coming, and this is the ground plate, and a jet comes out of this. Now, these jet subsequently break up into small droplets. This breakup is possible by two mechanisms. One we see here is that is Rayleigh capillary instability, other is the Coulombic instability. The first type of instability we have seen already, we have studied here in previous occasion. This instability will come into play when the charging of jet is not substantial. I mean not excessive, rather not I would say not excessive. So, this is this type of breakup of jet we have talked about. It is exactly the same one. Basically, you assume that the charge on the surface of the jet does not contribute significantly to this instability. Okay. Here in this type of instability, the drop diameter is close to 1.9 times the jet diameter, and drops are monodisperse. So, basically the Rayleigh instability that is considered for breaking of a jet, that has been modified for the presence of charge, and so people have done analysis in that line, and that type of breaking will happen when the charging of jet is not very high. So, in that case, there is the monodispersed drops are obtained where drop diameter is close to 1.9 times jet diameter. You know, we have already talked about this Rayleigh instability, how the drop diameter relates to the jet diameter. There would be a perturbation, that perturbation grows, and there is a breaking of jet into smaller droplets. So, this we have done a similar analysis, only the presence of charge has to be considered in that analysis, nothing else. The other type of breaking is referred as Coulombic instability. This is for excessively charged jet. So, this when the jet is excessively charged, that time such Coulombic instability will come in, and in this case the drops are polydisperse, and the jet undergoes Basically, in this case, jet goes through bending or whipping. Jet goes through these processes and the drops are polydisperse. However, here the drops are significantly smaller in size. Another thing you must appreciate here is that evaporation within drop. See, when the jet has come out of the capillary tip, there will be evaporation within the drop, and therefore there will be decrease in drop size. If there is evaporation, then automatically there will be loss, evaporative loss, and the drop size decreases. But charge does not decrease, so there would be increase in charge density. There would be increase in charge density, and as a result, if there is increase in charge density, there would be more possibility of this Coulombic fission. So, once the drop forms, it could be that the drop has formed by this the first one, first type of instability, but with evaporation there is decrease in drop, and then there would be increase in charge density. So, there would be further Coulombic fission, that means further breaking of drops. So, that this evaporation is the cause here. So, that you have to make note of. Now, when it comes to the spray mode, the spray of this, there are two ways it can be. Two distinct features can be observed here. One is called a pulsating mode, another is continuous mode. In pulsating, this is decided by the applied voltage and liquid flow rate through the capillary. So, these are primarily the two parameters, two variables that control the spray mode. And so, you have the two methods, one is pulsating, another is continuous. Now, what you have in pulsating spray mode is that the meniscus cone from the orifice oscillates during ejection of droplet from the tip. So, and on the other hand, the continuous, in the case of continuous spray mode, continuous jet disintegrates outside the capillary into droplets. So, in one occasion we see that if this is the cone, there is a meniscus coming out from the orifice, and then this is released, and then this meniscus goes back. So, meniscus cone from the orifice oscillates, meniscus cone comes out, forms a drop, and again it goes back, again another drop comes in. So, these drops are formed directly from this meniscus. That is a possibility. The other possibility could be a continuous jet coming out, and then that jet disintegrates into droplets. So, these one is referred as in this jargon that they are referred as pulsating spray mode, another is continuous spray mode. So, there is a difference between the two. In this connection, you must understand one thing is that there is a proposition here is that if this is the capillary, we are talking about this spray mode, we are talking about this pulsating mode. We have that means you are forming a cone here. Okay. Taylor has shown that if this is the capillary of say radius capital R, and then it forms a cone like this, then it forms a cone like this. So, this is the end of the capillary, and then it forms a cone like this, and these being the cone angle. This is the cone angle. Okay. So, he had there are scientific literature where it is shown that this cone angle approaches this cone angle. So, we are talking about this for this pulsating mode, this cone angle approaches to 49.3 degree for perfectly conducting drop and the liquid to gas permittivity ratio into infinity. So, for these cases this was shown that this cone angle will take a value of this. So, in fact cone angle can be predicted from the liquid to gas permittivity ratio. So, from these there would be, so if this is the end of the capillary tip, there would be forming a cone, and this cone angle will be a function of liquid to gas permittivity ratio, and these at the limit this is 49.3 degree. This has been shown shown by the researchers already. So, this is what we have as far as, so these are the two modes that we talked about, and this is all we have as far as the use of DC electric field is concerned in forming the droplets. Now, there are certain concerns in using DC electric field, because next what we would be talking about is the AC electrospray, and there are certain concerns in using this DC electric field. These concerns are, I can see, number one is gas bubbles from electrolytic reactions to balance the charge induced by the applied voltage. So, that is one concern which is already I mean, we understand this, that is not a that is understandable. Second thing is Joule heating, because it is a DC field, and generation of other chemicals due to Faradaic reactions at the electrode. So, these are some of the concerns of DC electric field for which that there was an interest in using the AC field. Now, if we look at this AC electrospray, there are a couple of main issues that I would be touching upon, because otherwise this method is same and you have this relaxation time, and then there would be critical voltage and all, everything would remain same. Only thing added on top here is the importance of AC frequency. Okay. So, importance of AC frequency, what we meant here is that there exists another time scale. So, that is this time scale, there is another time scale which is coming, which is from the electric field itself. I mean, if I try to revisit that issue once again, the charges transferred into the liquid bulk from, of course, from electrode, the charges transferred into the liquid bulk from electrode with its own relaxation and accumulation time we showed that this is of the order of 1 microsecond. Okay. Now, here you are imposing another AC period, that means you are applying the voltage for certain time and for other times you are not applying, I mean you are going the other way. So, if this AC frequency is if AC frequency is less than 1 divided by this relaxation time we are talking about, so if the AC frequency is less, if this AC frequency is less, see there is an issue. It could be that we are looking at a local distortion of meniscus. That means there is, I mean you are applying a voltage, but you are moving away from that voltage so fast that simply the meniscus has distorted locally, but it has not gone to the culmination within that time frame. Culmination means forming of a complete drop and going out. So, you have to ensure that this voltage is applied for sufficient time, so that the you are not simply talking about the local distortion of the meniscus. Okay. So, this AC frequency is linked with both these aspects. One is towards this AC frequency has to abide by the demand from that charge relaxation point of view, and this AC frequency also has to be in tune with what is the viscous time scale, because it is, if it is just a local distortion of meniscus, that will not be sufficient. So, what we would be looking at this point probably is something called the RC time scale of double layer. That is something which we have to look into. Now, if we try to understand what is the RC time scale of double layer, then what we have to do here is we need to understand how this double layer works here. Typically, double layer is modeled as a capacitor with capacitance per unit area is equal to epsa divided by lambda d. Epsa you know is permittivity and lambda d is the thickness of this double layer. Now, this double layer, so in that case double layer, I mean ideally, I mean double layer the way it is looked into is, if you consider this as an AC impedance, that is the ideal way of handling double layer, because in that case you will, if you have an input signal something like this, where I is equal to this quantity. So, if you give an input signal where V naught is the amplitude of the signal, where V naught is the amplitude of the signal and V t is the potential at time t, and omega here is equal to 2 pi f is the angular I mean basically it is associated with the angular I mean defines the angular frequency. In that case, what we will do, in fact, we will continue this analysis. What we will do is we will find out the corresponding response signal, which is called an response signal. So, V t is an input signal stimulus, and this is the response signal we will calculate, and then we will calculate what is called a complex impedance. So, I mean this is a very standard exercise for electric circuits. What we are trying to we will try to find out what would be the RC time scale of a double layer, and that has to relate to the AC frequency. I will try to at least touch upon the various issues in the next lecture, and then we will continue understanding this electrospray process, and there is another very interesting phenomena which is very close to this kind of this use of electrode and producing flow out of it. So, that we will touch upon in the next lecture. Thank you very much.